Hi everyone, and welcome to this first ECON 333 lecture of the spring term 2022 semester. Today we are going to talk about some fundamental probability concepts because these are the concepts we need to able to understand how statistics work, how statistical theory works, and how we can propose accurate estimations and predictions based on some data that we observe. Before we start, I want to mention that I do not legally allow this content to be published without my consent. In this sense, I mean that I do not allow this content to appear anywhere else than on your Canvas page for Econ 333. You are free to download this content and use it for yourselves. However, I do not legally allow its publication on other platforms and websites. If I see it online, I will take it down and report whoever uploaded it. So, the outline for this first lecture. First, I will talk about what a random variable is and what a probability is. We all have a fairly good understanding of what they are, but it is important to understand what the definition exactly is so that we know what we are talking about. Then I will talk about probability distributions and moments. So I will talk about how do we express a probability, how do we compute a probability, as well as how do we compute relevant measures related to probability, something like expectation, variance, and later we'll talk about covariance, correlation, and so on. I will cover different distributions and moments for discrete random variables, as well as continuous random variables. The concept of a probability is slightly different when we talk about a discrete random variable versus a continuous one. To build those notes, I heavily borrowed from the book by Stock and Watson. This is the recommended book for the course, and in particular, I used some of the content from chapter 2.1 and 2.2. So this is something you could look at if you are confused about anything and we are not able, the TAs and myself, to explain this concept in a way that you understand. So let's start with what a random variable is. A random variable, and I will use RV for short throughout the whole course, is a variable whose value, which we also call a realization, depends on outcomes of a random phenomenon. It is generally denoted by the uppercase letters X, Y, Z, or U, V, while the realization of these random variables are typically denoted by lowercase letters, small x, small y, small z, and so on. An event is a set of one or more outcomes. Since we talk about random phenomena here, then we will talk about some kind of random events. Note that in the word random variable, there is the word variable. So if you think about mathematics, a variable is typically what you're looking for in an equation, the variable x, the variable y. In mathematics, however, the value of the variable is deterministic. There is a specific value which is going to satisfy your equation. In probability, this value, this variable, does not always take the same value. And this is a fundamental difference between the deterministic people who do pure math, and probabilistic people who are including some random, some chaos in these equations and in these mathematical concepts. Imagine an event like obtain heads 5 times out of 7 coin tosses. You have your coin, you flip a coin 7 times, and one of the possible events is you obtain heads 5 times. Well, this event could come from many different outcomes. You're just counting out of 7 how many times you got heads. But there are different outcomes that can lead to that same count at the end of the day. For instance, you could actually do 5 heads in a row and then 2 tails. This is one possible outcome. Or you could do 3 heads, then 2 tails, then 2 heads. And if you sum up the number of heads, again, it's equal to 5. These are two different outcomes leading to the same event. In fact, if this course was more focused on probability theory, we could use some formulas called Combinatorics Formulas to figure out exactly how many outcomes correspond to that event. Here I just gave you 2, but another one would be to have heads, tails, heads, tails, heads, tails, and tails. Again, if you count, you would get heads 3 times. Or tails, 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 and then heads, and so on and so forth. Unfortunately, this course is not about probabilities only. That's too bad because combinatorics are very fun, but it is very, very complicated. We typically distinguish 2 types of random variables. Random variables can either be discrete, they take a a discrete number of values, 0, 1, 2, possibly infinite, but we don't have any decimal places, or they are continuous, as in there is a continuum of possible values. Typical example of a discrete random variable, the age or the number of kids of the next person you meet. This is random. Person A could have no kids, and person B could have 3 kids. But we never count kids as 1.5. Or the number you obtain after throwing a die. You have a 6-faced die that you throw. You can obtain either 1, 2, 3, 4, 5, or 6. There is no such thing as a 2.5. Or it could be any type of scoring obtained at a roulette, a blackjack table, or in general, any gambling game. Continuous random variables are all these variables that are divisible in real life. If you think about weight and height, we don't only say that some people are 5.5, 5.6, and so on. Technically, we can have a lot of different decimals in the middle. For the weight, we might stop at 155 pounds, but in reality, if we had a scale that is infinitely precise, we would have a lot of possible decimals. And exactly 150 pounds would not be the only value that you would get. What we observe in reality is actually a round-off version of that. The temperature is the same thing. Now, we also distinguish qualitative variables and quantitative variables. Qualitative variables are, as the name suggests, qualitative. They are not about numbers, they are about characteristics. For instance, I could ask you, do you like tea? Some of you might say yes, some of you might say no. This is a random variable. The taste of people is random. One person might like this, but another person might not like it. Same as, is the next person I'm going to meet a man or a woman? Yes or no? Or is the next person I'm going to meet a smoker or a non-smoker? Does the next person I'm going to meet take the car, take the bicycle, or the train or the bus, or maybe some combinations of them? What we typically do when we deal with qualitative variable is we turn them into a quantitative variable. For instance, we could code 1 for man, 0 for woman, and it's not about who gets the 1 and who gets the 0. You could do it the other way around as well and give 0 to a man and 1 to a woman. But the idea is to say the variable x can either be equal to 1, that's when I observe a woman, or 0 when I observe a man. And this way, we are going from a qualitative variable back to a discrete random variable. This will be particularly relevant once we deal with R. R will be able to read yes and no, but R does not understand yes and no as a number. So somehow R has to kind of code these letters into some kind of a number, because at the end of the day, a computer only understands two things, 1 and 0, the binary language. In fact, the number, let's say 237, can be expressed in binary language. It is going to be a sequence of ones and zeros. And if you have the key to read binary language, by looking at a sequence of 1 and zeros, you'll be able to tell, oh, this means this number. Now, we know what a random variable is. Let's turn into what a probability is. Well, a probability is a number that represents the proportion of the time an event occurs. Note that here I am talking about an event. So, for an event A, we typically denote it P of A. Note that this P is kind of fancy. This is just a P with 2 bars on the left. That's just a conventional notation. But if you only write P in the midterm or the final, as long as it's a big P, no problem, you're good to go. Couple of examples. An event could be get a number bigger or equal to 3 if you throw a die. So, when you throw a die, you can get either 1, 2, 3, 4, 5, or 6. So the probability of getting a number bigger or equal to 3 will be the probability of getting either a 3, a 4, a 5, or a 6. What we do in this case is we count the number of times we will see a success. This is bigger than 3, this is equal to 3, this is bigger than 3, and we will divide this by all the possible outcomes or cases. There are 6 possible cases, and 4 of these cases will correspond to the number is bigger or equal to 3. So the probability of getting a number bigger or equal to 3 will be 4 over 6. Number of successes divided by the number of possible cases or outcomes. I really want to emphasize the distinction between what an outcome is and an event. Do not mix them up, or you will only get partial marks in exams. Now let's take another random variable, which is continuous, because here x denotes the weight of a person. An event could be the weight of the person is bigger than 150 pounds. Then in this case, P of A is the probability that a person weighs more than 150 pounds, strictly more. Now, what happens if you have 2 events at the same time? If you're looking at 2 events at the same time? The intersection of 2 events A and B is the case where both event A and event B occur at the same time. And we typically denote it A and B with this kind of N, which is just an upside down U. And we typically call it A and B. So the intersection is when both happen at the same time. The union will be when one or the other or both at the same time occur. And we will denote it A, U, B. A or B. This, take it as the U of union, and this, take it as the N at the beginning of intersection. That's pretty much how I learned back then. Now, two events A or B are said to be disjoint if they cannot happen at the same time. So, the probability that both A and B happen at the same time will then be 0. Imagine, for example, that we call the event A get an odd number when you throw a die, and B is the event corresponding to get an even number. What is the probability of A? What is the probability of B? Well, if you throw a die, six faces, the probability of getting an odd number is the probability of getting either a 1, a 3, or a 5. We have 3 successes out of 6 possible outcomes. So 3 over 6 will be equal to 1/2. That's the idea that half of the numbers on the die are odd and the other half is even. Now, what is the probability of getting an odd number and an even number at the same time? You can imagine that, well, if you throw one die, you only get one number at a time, and a number cannot be even and odd at the same time. It is impossible. It's either one or the other. So, the probability of A and B happening at the same time will then be equal to 0. Now, what is the probability of getting an even or an odd number? This time, we are looking at getting either one or the other. So, if I get a 1, it's an odd number, it's a success. If I get a 2, it's an even number, it's also a success. If I get a 3, it's an odd number, it's a success, and so on. So whatever number you get in this case, then you either get an odd number or an even number, and so A will be satisfied, A will happen, or B will happen. But one of them will always happen. So the probability of A or B is actually equal to 1. There is a 100% chance that we will get an even number or an odd number. And you're right, the second one here is the probability of the intersection of two disjoint events. Since we cannot get an odd number and an even number at the same time, then the event A and B are disjoint, absolutely. Careful, however, because I could say A is the event getting an odd number in the first throw, and B is the event get an even number in the second throw. In this case, these events are not disjoint anymore, because I could get an odd number in the first throw and an even number in the second one. So the wording is actually sometimes challenging when we talk about probabilities, and this is why I really want to take my time to define all the terms today. Imagine we have a third event, C, which corresponds to you get a 3. What is the probability of B and C? Well, the probability of B was get an even number, okay? And what is the probability of C? C here is get a 3. One event, the event C, is smaller than the event B. B covers the case of getting 1, 3, and 5, but C only covers the case of getting a 3. So this probability will actually be equal to the probability of getting a 3. Because you need a 3 first, and since 3 is odd, then the event B will automatically be satisfied once you have a 3. But if you get a 1 or a 5, B is satisfied, but C is not. And so there is a lot of logic to apply to probabilities. The notation might seem kind of cumbersome, annoying, but we need some of this mathematical notation if we want to uncover more properties about probabilities. So make sure you are okay with the definitions. You will need to know them by heart for the exams, and you will apply them in the assignments and in tutorials. So, I talked about events that happen at the same time, events that one could happen or the other could happen, or both at the same time, that could work too. This is what we call the union. I talked about disjoint events. Now, let's talk about independent events. Two events, A and B, are said to be independent if the realization of one does not affect the probability of the other. So the probability of A happening is not influenced by the probability of B happening. You can find some of these definitions in the textbook, yes. You can also find some of them in Wikipedia. Those definitions are pretty much the same everywhere, and I picked the one that seemed the easiest and the simplest. Some events are likely correlated, like drawing a king in a first card draw and drawing a second king. If you do not replace the first card in the deck, this will affect the probability of getting another king, because now you only have 57 cards to draw from. But if you think about throwing a coin twice in a row, well, the second throw will have absolutely no correlation with the first throw. You throw once, heads, you write it down, you throw a second time. These things are totally independent. So, pay attention, make sure you are able to tell whether two events are independent or not, because there are going to be some mathematical results that will come out of that you might need to use. Some events are naturally correlated. If you get a heads or a tails on a single coin toss, means that you cannot get the other. If you get a heads, then the probability of getting a tails is going to be 0 because you already got heads. It seems trivial, but again, it's important to be able to recognize when two events are independent or not. Other events are totally uncorrelated. Think about the temperature in Vancouver and the sales of a supermarket in the beautiful town of Asparin, which is where I am right now. Feel free to type it on Google Maps to get an idea of where it is. Well, the temperature in Vancouver right now is rather cold, I heard. And it's pretty unlikely that the temperature in Vancouver will affect the sales that my local supermarket makes every day. Now, maybe if I talk about Burnaby instead of Asparin, there could be some kind of relationship, because the temperature in Vancouver might have an impact on the crops in the area or on the returns of fishing. Maybe fishermen will have more trouble to fish so there'll be less salmon that day, and the price of salmon at Safeway in Burnaby might be higher because of that. So there are some events that maybe look uncorrelated, but sometimes there could be a third event in the middle that might be a link between the two. In fact, there is a very funny website called Spurious Correlations that reports a lot of different statistics about two things which are totally uncorrelated, but when you look at the correlation formula, it's actually incredibly strong. That's just a result of how the numbers look. And this is just a formula at the end of the day. And sometimes the numbers are such that the correlation formula reports a very high correlation result, but obviously those two different measures are not correlated at all. I really recommend you to take a look at this website, it's pretty funny. And it's part of our job in economics to figure out if two events or two variables are correlated, or if maybe we thought they were, but this is just a coincidence with the statistics. A couple of basic properties about probabilities. These will turn useful, especially when you want to double check your results in an exam or in an assignment. First of all, probabilities are always between 0 or 1, or between 0 and 100%. As obvious as it seems, we, instructors, see on a very regular basis students report negative probabilities or probabilities bigger than 1 and just report them as if nothing was weird. If you do find something that doesn't make sense in an exam, it's actually a good thing to write down that doesn't make sense. There must be a mistake somewhere. If you don't have time to correct your answer, at least you can report that it doesn't make sense and that you're aware that there's a mistake somewhere. That could get you a couple of partial marks. Probabilities add up to 1 or 100% over all the possible outcomes. So if you throw a die, you can get a 1, 2, 3, 4, 5, or 6. Overall, if you add the probability of getting a 1, of getting a 2, of getting a 3, and so on, you will get to 100%. Because if you add all these probabilities, you end up with the event, get a number between 1 and 6. Well, those are the only possible numbers I can get with a die. If you toss a coin, and you add the probability of getting heads and the probability of getting tails, you're going to get 100%. In fact, it's not technically 100% because there is always a chance that the coin lands on the side and stays vertical. It's a tiny chance, but we have seen it before, right? Not me personally, but you can probably find videos where this happens. Now, let's take an event called A. The complement of A, which will denote AC, C for complement, or A bar, so it really depends on your favorite notation. Personally, I prefer A bar, that's just how I learned it, is the opposite of A. So if you think about the event get a 1 when throwing a die, then A bar, the complement, would be get anything else but 1. So if you add the probability of getting a 1 and the probability of getting anything else but 1, that gives you the overall set of possible outcomes. So the probability of A union the complement of A will be equal to 1. So you could take P of A here and put it on the left hand side so that when you add these two probabilities, you get 100%. This might prove useful. I could ask you something like, what is the probability of getting at least a 2 or something like this when you throw a die. You could say, well, yeah, there's the probability of getting a 2, 3, 4, 5, 6. Or you could say, well, it's 1 minus the probability of the opposite. What is the opposite of at least 2? This is 1. So, getting at least a 2 is the same as 1 minus the probability of getting a 1, which is 1 over 6. And that makes computations faster. It is also a good way to double check your results. If I ask you to compute a given probability, you can go through the complement to double check that you found the same results. If you didn't find the same result, then chances are, well, one of them is wrong. Chances are maybe both are wrong, but at least it tells you that you will not get full marks on that question. An important property is the probability of the union of A and B. This is actually equal to the probability of A plus the probability of B minus the probability of the intersection. The idea is that when you look at the probability of A plus the probability of B, you are already counting the probability of the intersection once. Well, actually twice. If events A and B overlap in some way, then when you look at the probability of A, inside you are including the probability of B happening at the same time. And when you look at the probability of B, inside you're also taking into account the case where A happens at the same time. Since you count this thing twice, you want to remove one of them, and this is why we have the minus the probability of A and B. This is best illustrated with Venn diagrams, which you can look you can look up online. I don't have any for these lecture notes. It's fairly intuitive, and again, this is a property you should know by heart. Now, as I mentioned before, if A and B are disjoint events, then the probability of both happening at the same time is 0. So, if you replace this by 0 here, then this formula goes down to probability of A or B is equal to the probability of A plus the probability of B. So if you know that A and B are disjoint, then this formula simplifies to just adding the probabilities. And if you have another event, C, and you say A or B or C or D and so on, then you just have to do the probability of A plus the probability of B plus the probability of C plus the probability of D and so on and so forth. If the events are not disjoint, though, you're going to need to remove these intersections every time. If you have 3, 4, 5 events, that get pretty painful. Not difficult, but painful. Long. Now, I just gave you the basic ideas of what a random variable is and what a probability is. If you want to fully characterize a probability, we need to talk about a probability distribution. Moments are relevant measures about the random variables. Here, we need to distinguish between discrete and continuous random variables. So bear with me for a bit. There's going to be a bit of jargon. This is not going to be something that you will remember right away. You're going to have to read about it over and over again to be able to understand the distinction between all those terms. They sound a bit alike, so you need to make sure you can distinguish them. The probability mass function of a discrete random variable is the list of all the possible values of the variable along with the probability they occur. Note that here I talk about the list of all possible values. So if I throw a die, I need to say, well, I can get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And then I need to specify what is the probability of getting each number. This is what we call a probability mass function. We need to detail the whole list. So, the probability mass function of a die throw is going to assign a probability of 1 over 6 to each number that we can obtain. There is a mathematical way to write it down. Don't worry about it. You can use words. I mean, it's the same thing. But you need to specify all the possible values, and for each value, what is the probability that the random variable is equal to that value. This is why we use the term mass, because we can get one number with a given probability, so there is a mass on it, a probability mass. If you think about a fair coin toss, then you can get heads or tails, each with probability 50%. Along with the probability mass function, the PMF, we will have the concept of a CDF, a Cumulative Distribution function. As the name suggests, we are going to cumulate probabilities up to a certain point. So the CDF is the function that gives the probability that a random variable is lower or equal to a particular value. For instance, the probability that a die throw returns a number lower or equal to 5, which we will write the probability that x is lower or equal to 5. Why do we say it's cumulative? Because we need to take all the possible events that are going to be satisfied. Since x should be lower or equal to 5, we are going to add the probability of getting a 1, the probability of getting a 2, the probability of getting a 3, the probability of getting a 4, and the probability of getting a 5. That gives you 5 out of 6 possible outcomes. So the probability of getting a number equal to 5 or less will be equal to 5 over 6. As soon as you see the probability of being equal to a number, we will talk about the probability mass function. As soon as you see a lower or equal, a bigger than, or any inequality sign, then we will be looking at a cumulative distribution function. Now, the reason why we make a distinction between discrete random variables and continuous random variables is because if you think about a continuous random variable, that is, the unit is infinitely divisible, then technically the probability of getting exactly a specific number is equal to 0 because there are infinitely many values. So the probability that the next person I meet weighs 150 pounds exactly, 0.000000000, is going to be one chance out of an infinite amount of chances. Because there could be 150.0000001, 150.010001, and so on. So when we talk about a continuous random variable, it doesn't really make sense to talk about a probability mass function, because there is no probability of getting one specific value. However, we will use the concept of a probability density function. The probability density function, or PDF, is the function representing the relative likelihood or relative probability of a value a random variable can take versus other values. And if you look at the area under the PDF in between 2 points, you will obtain the probability that your random variable falls in that specific interval. I will show you in detail how this looks like once I'll talk about distributions. Like common distributions, the ones we are manipulating on a daily basis, and the ones you, will be manipulating in this course. So, we don't really talk about the probability mass function, but the density function is saying how more likely it is relatively to get a value equal to this as opposed to another value. Again, 150 exactly getting 150 pounds has a probability of 0, but it might be more likely than finding someone that weighs 250 pounds. Why? Because the majority of the population is around 150 pounds, between, let's say, 120 pounds and 180 pounds. So it's relatively more likely to find somebody at 150 than somebody at 250 or at 40 pounds. The cumulative distribution, however, the CDF, will be the same thing. It is the function that gives the probability that a random variable is lower or equal to a particular value. The probability that the next person I meet weighs less than 150 pounds is not 0. There is a chance. Because lower than 150 pounds, there are a lot of possible numbers. Same with above 150 pounds. Same with between 150 pounds and 170 pounds. Now, let's quickly move to some moments. The expectation of a random variable, which we typically denote big E of x, again, with these two vertical bars for the E. We often call it mu, or mu with the subscript x, to say this is the expectation of the random variable x, is the average value that x will take. So when you hear expectation, think about mean, average. If a random variable is discrete, the expectation will be the sum of all the values it can take times the probability of taking that value. This is the summation symbol with indexed by I, where I goes from 1 to n. So in this case, there are n possible values that x can take. Value times probability it happens, plus value times probability it happens, plus value times probability it happens, and so on, until you go over all the possible values. For a continuous random variable, again, since this thing is actually equal to 0, the average weight of a person is not 0. So we need to redefine the notion of expectation. And this summation symbol, the Greek uppercase sigma, turns into this light wavy S, that's also an S, where we are going to sum from the minimum value x can take to the maximum value. Here I assume from minus infinity to infinity. Again, we're going to multiply x by, not by the PMF, but by the PDF. Now this here is called an integral. Do not be worried about what it means and how to compute it. I will not ask you anything about it in this course. This is a calculus 2, maybe 3 concept that maybe some of you have studied already. This is not a concept that we require econ students to know in the undergrad program. So I just wanted to show you how we actually compute it when the variable is continuous, but you will not have to know it. So you can already forget about it. But I just love integrals. I'm a bit nerdy. I love integrals, so I kind of wanted to show what it is and what it means. So let's take a sixth-faced die throw. And x, again, is a number. X should always be a number. So here, I'm going to say x is the obtained number when I throw a die once. Then, with a probability of 1 over 6, I can get a 1. With a probability of 1 over 6, I can get a 2, and so on and so forth. I add up all of these numbers, and I get that on average, the number I get by throwing a die is equal to 3.5. Now, you know that it is impossible to find 3.5 in one die throw. No die throw will ever give you the number 3.5. It's either 3 or 4. There's nothing in the middle. So, the average or the expectation is not necessarily something we can obtain. If your wage is variable, it varies from, I don't know, let's say on some month you get $3,000 and other month you get $4,000. If somebody asks you how much are you making over a year, you can give the full wage, or you could say, well, I don't get paid the same every month, but on average I get paid $3,500. You do not actually get a paycheck of $3,500. Sometimes it's $3,000, sometimes it's $4,000. So the average is not necessarily something we can get or obtain. Quickly, let's talk about the properties of the expectation. Let's take two random variables, x and y. They can be discrete, continuous, it doesn't matter. And let's take two constants a and b. Then we have the following properties. If I multiply my random variable x, that should actually be a big X, my bad, by a number a, on average, it is equal to simply multiplying the average of x by this number a. You can do it here actually. If instead of saying, well, x is the number I get from a die throw, you could say x is the number I get from a die throw times 2. So you just multiply each of these numbers by 2. So here you get 2, here you get 6, and so on and so forth, and here you get 12. If you do the math, you will find an average of 7. 7 is also equal to 2 times 3.5. So it's also equal to 2 times the expectation of x. And this is what this property is saying. Since a is a constant and we'll multiply every possible number we get by a, then it's the same as multiplying the overall average by a. Since a is not random, it's always equal to the same value, we can simply put it out of the expectation. We cannot put big X out of the expectation because big X doesn't take a certain value 100% of the time. Sometimes it has one value, sometimes it has another. And this is why we need to have it inside the expectation symbol. Now, if I have 2 dice, and I throw them independently, one with my left hand and one with my right hand, and I add the numbers together every time. Well, since my throw are independent, they don't affect each other, then I can take the sum, and the average sum is the same as the sum of the averages. This is what we call the linearity. When you have a plus or a minus here in the middle, you can break up the expectation into expectation of the first term plus or minus, whatever this sign is, the expectation of the second random variable. Now imagine that I look at the number 2. I do something, but I always obtain the number 2. There is nothing random about it. So what do I get on average? Well, on average, I'm going to get the number 2, since I get number 2 every time. So when a number is not random, when a variable is not random, then its expectation is equal to itself. Now, do not mistake this plus with the union we saw earlier, the U we saw earlier, because the U was inside a probability. Inside an expectation, you will rarely, if not, probably never, see a U or an N. Because in this case, we will say, well, let's call this thing another variable Z. So do not take this as an interpretation or an analogy to the U from before. It is not the same thing anymore. Here, we are strictly speaking talking about the mathematical formula that I show here. Note that this is a sum. So if I replace x by x plus y, I can just expand the sum, and I get sum of xip and so on, plus sum of yip and so on. And so you can break up the sum into two smaller sums. And this is what we get here. This big sum here can be broken into two smaller sums. And the last one is also kind of a tricky one. When you have the plus, you can break the expectation up. But if you have a multiplication here between two random variables, you cannot break it into the product of the expectations most of the time. And when I say most, I mean easily 99.99999% of the time. It's only in very specific circumstances that this equality will hold. So when you multiply two random variables, well, you need to look at the probability of x being equal to some value and y being equal to some value at the same time. And then the distribution, the PMF, this part, is going to get messy. I will show you an example of this in the next lecture when we deal with two random variables at the same time. For now, I just wanted to make it simple for an introduction. We are only dealing with one. Now, bear with me, we're going to have a break soon, but I have 2 more slides, so that should cover that lecture. After talking about the expectation, I want to talk about the variance. The variance is something you are familiar with as well already, but I still want to show you the kind of fancy formulas to give you a systematic way to approach computing a variance. The variance, which we denote Vx, and the left bar of the V gets 2 bars, if you want to, otherwise you just put a straight V, that's totally fine for me, which we often denote sigma, little sigma squared, and I'll show you why we use a squared, is, in words, the expectation of the squared deviation from the mean, or the expectation of the squared deviation from the expectation. I love saying this because it's so confusing. We need math to make it more clear. So, first of all, we have, go back from the end, use backward induction. That's kind of what people do in game theory. Look at the deviation from the mean. Deviation from the mean means I take my x and I take the difference between the values it can take and the average value it takes. Deviation from the mean. And then it says squared. So I take the square of this number. And finally, because this is random, x can change. Sometimes it's equal to 1, sometimes equal to 3, and so on and so forth. So I'm going to take an expectation out of that squared deviation from the mean. Because I take an expectation, I can actually go back to the previous formula. The previous formula was saying sum of the value times the probability it happens. Now, we do not have expectation of x here. We have expectation of x minus expectation of x squared. So, we're going to replace our small xi from before and just have it there. And multiply by the probability that x takes the value xi every time. So, if you look at it here we have just x, so that's why you have xi, all the possible values you can take. But now, since I don't have x alone anymore, I have this x minus expectation of x squared, then I need to replace by xi minus expectation of x squared. And the rest doesn't change. You will see that in practice, it's actually easier to compute, but I need to give you the formal definition. The standard deviation of x, which we denote sigma without the square, is the square root of the variance. So we take the square root of all this. So since you take the square root of sigma squared, you go back to sigma alone. And this is why the variance has a square, because we have a square here, whereas the standard deviation takes the square out by taking a square root. Note that you cannot just take the square root here inside. You have to take the square root before the summation sign. This is a very common mistake. So if you want to compute the standard deviation, no shortcuts. Find the variance first. Do this computation, and then, only then, once you get your number, take the square root. With this, you will never go wrong. Now, this formula is kind of a pain. Honestly, myself, I might have used this formula, I don't know, twice or 3 times in my life because I had to. There is another formula which is very convenient, which is exactly the same. I do not want to prove how you can get that formula. It is not very complicated. Expand the square here, take the expectation, use the fact that you can break the minus into separate expectations, and stuff is going to cancel out. And you get this lovely formula. Now again, there is often some confusion about where the square is being put. So the variance of x can be expressed as the expectation of the square of x, minus the square of the expectation. Expectation of the square, so I say what's outside first, expectation of the square, minus, here what's outside is the square of the expectation. If you want to compute this number, you can use the formula we saw before. Here, however, you would have a square. So the only thing that would change is here you put a square. And nothing else changes really. So it is the same process as before, but now you take the square of the values xi every time. Then, since in principle you will have computed expectation of x already, simply take the square. That is pretty easy. And finally, take the difference. That and that will be exactly the same. Now note that the formula I show you here is only for the case of a discrete random variable. This formula works for both discrete and continuous, but this one is only in the case of discrete. If you want the continuous variable equivalent, well, you have to turn this into an integral. You have to put this wavy s. Then you would have this here would not change. Then you would have this that becomes the PDF, the density function, and then you would have this weird dx at the end, which is just notation, nothing to be too worried about. But again, you will have to know it. The square of the expectation is not going to be the same as the expectation of the square. No. If you want to verify this result right now, you can do, open the brackets, you do 1 plus 2, and then you take the square. So outside of the brackets, you put a square, and you look at the result. Then you look at 1 squared plus 2 squared, and look at the result. And let me know if you have exactly the same. One plus 2, everything squared, and 1 squared plus 2 squared. The idea is that the sum of the squares is not the same as the square of the sum. The same way, the square root of the sum, square root of 1 plus 2, is not the same as square root of 1 plus square root of 2. And why is that? Why can't we invert the order? Why can't we flip the order? That's because the square and the square root are not linear. The sum is linear, which is pretty much what we have here, and expectation is a sum. So that's pretty easy. So the expectation of the sum means I take the sum of a sum. So this is the same as the sum of a sum reversed. And be very careful. It is very often a source of mistake by students. So in the problem sets and in the next lecture, I will do some examples that I strongly suggest you to try again at home, grind them, until you can compute those things fast. Because those things are not inherently difficult to compute. You just have to get used to it. Same as when you learned what derivatives were the first time. The first time you're thinking, oh my god, what are those formulas? The product rule, the chain rule, the division rule, I guess it's called in English, I'm not sure. It's complicated. Then you learn them by heart, you grind them, you eat them for breakfast, and eventually you can do calculus like this on a regular basis in your head if you have to take a class like 302 or 201 or 305. Same thing here. It could be a painful process, but after doing it, I don't know, 10, 20, 30, 100 times, then it's going to become automatic and you will never make mistakes. Consistency is key. It's like training for anything. You need to practice again and again and again if you want to be good at it. So, I'll finish with the properties of the variance. Because of the square here, the unit of the variance is expressed in the square of the unit of x. So if x is the weight, and I want to look at the average weight, well, I can say the average weight is 140 pounds. Okay. But if I look at the variance of weight, it gives me a number which is equal to the square of the weight, which is not very convenient to use. And this is one of the reasons that we take the square root. By taking the square root, we take the square down, and the standard deviation is expressed in the original unit. So a standard deviation could be something like 10 pounds. This means that on average, people are 10 pounds away from the average weight. If the average weight is 140 pounds, on average, people are 10 pounds above or under. And again, it's an average. Everybody is different. You guys might be 1 or 2 pounds away, or maybe 20 or 30 pounds away. On average, that would be 10 pounds. This is what the standard deviation tells you. Same as a grade distribution. I know that many of you are interested in knowing the average grade in a course and the standard deviation. The average grade would be, 70%, 60%. The standard deviation could be 15, 20%, which means that students on average are 20 or 10% away from the average, which could be above the average by 10 or 20% or lower than the average by 10 or 20%. This is a measure of dispersion. It tells us how spread out, how volatile, how much a distribution varies. And we'll see this in the properties. The second formula, in general, is more useful for random variables that only take a few values, because you can compute the expectation of x very easily. You can compute the expectation of x squared very easily, and then you finish the formula. And I will show you that in the first tutorial. So again, let's go back to two random variables x and y, and two constants a and b. Now, if I multiply my random variable by a, I can only take a out if I square it. So the constant can come out, but since in the variance we are looking at a square, instead of just putting a out, we need to square a. So looking at the formula, imagine that here I multiply x by a. So I have an a here and a here. I could factorize and put the a between the square bracket and the round bracket. But if I do this, I am taking the a out of the square. So I would have to take a squared out. And then, since it's an expectation, I can take this a squared in front of the expectation. The variance of a is 0. Why? Because a is a constant. So the average will be equal to a. And going back to the formula, if the average is equal to a and x always takes the value a, then we are going to get a minus a plus a minus a plus a minus a plus a minus a. We are going to get a sum of zeros. And the variance will be equal to 0. The only case where the variance of a random variable is equal to 0 is where the random variable is not random. It's a constant. If, for instance, in the midterm, everybody gets 80% in the midterm, then what is the average? 80%. What is the variance? Well, if everybody gets 80%, the variance will be 0. There is absolutely no variation in the grade distribution. Again, this is a useful way sometimes to make computations fast. And if you find a variance of 0 when your random variable is actually random, then you made a mistake. You will necessarily find a positive number, because it's a square every time. So you're adding up squares and you multiply them by something which is between 0 and 1. The variance is always a positive number, and this is why we can take the square root. The square root of negative numbers doesn't exist when we use real numbers. It exists in the whole of the sphere of mathematics, which we will not talk about in this course. So, if you find a negative variance, red flag, something's going on. If you find a variance of 0, but the variable is supposed to be random, red flag, you got something wrong. And finally, can we break up this plus when we look at the variance of the sum of two random variables? Well, we can, but if you do, you need to also include another term called the covariance between x and y. This is a measure I will talk about in the next lecture, where we deal with more than one random variable. But again, remember that since we have a square, because it's a variance, look at x plus y squared. It is not equal to x squared plus y squared. There is a double product. A plus b squared equals a squared plus 2ab plus b squared. Here, it is the same thing. This double product in the middle takes the form of a covariance. But the 2 is there. The double product is there. I think that's enough for this first lecture. Have a good rest of your week, and see you in the next one. Bye.